The average gardener or small-scale farmer spends hundreds, sometimes even thousands of dollars every year on fertilizers, watching their hard-earned money literally dissolve into the soil while at the same time degrading the very ecosystem they're trying to nurture. Synthetic nitrogen fertilizers have created a vicious cycle of dependency where soil becomes increasingly lifeless and reliant on outside inputs, water systems suffer from nutrient runoff, and the environmental cost just keeps mounting with each application. But what if I told you there's actually a way to produce the equivalent fertility of several tons of commercial fertilizer right on your own property, while also building soil structure, increasing water retention, and creating habitat for beneficial organisms? This isn't just theoretical. I'm talking about systematically cultivating 6 tons of nitrogen-fixing biomass every year, a practice that can completely revolutionize how we think about soil fertility and agricultural sustainability. So, nitrogen is actually the most limiting nutrient in most agricultural systems, which, honestly, is why it dominates fertilizer formulations and why farmers all over the world spend billions purchasing it in synthetic forms. The production of synthetic nitrogen through the Haber-Bosch process, by the way, consumes roughly 2% of global energy and contributes significantly to greenhouse gas emissions. Once applied, a lot of this nitrogen ends up leaching into waterways, creating dead zones in oceans and contaminating drinking water supplies. The rest volatilizes into the atmosphere or, well, just temporarily feeds plants before being depleted, requiring yet another application. This linear system of extraction, production, application, and loss is fundamentally unsustainable, yet we've built our entire food system upon it. Nature, however, offers an elegant alternative that's been operating successfully for hundreds of millions of years. Certain plants, primarily in the legume family, but also including specific trees and shrubs, have evolved symbiotic relationships with soil bacteria that can capture atmospheric nitrogen and convert it into plant-available forms. This biological nitrogen fixation happens continuously, costs nothing, requires no fossil fuels, and builds soil health rather than depleting it. The key to unlocking this natural fertility isn't just growing a few nitrogen-fixing plants here and there, it's systematically cultivating massive quantities of these biological nitrogen factories and strategically incorporating them into your soil. When you grow 6 tons of nitrogen-fixing biomass, you're not just adding organic matter, you're creating a nitrogen reservoir that can sustain intensive food production for an entire growing season, or, honestly, even longer. Achieving 6 tons of biomass production requires selecting species with exceptional growth rates, substantial nitrogen-fixing capacity, and adaptability to your specific climate and soil conditions. For most temperate regions, a combination approach works best, utilizing fast-growing annual legumes for quick biomass production alongside perennial nitrogen fixers for sustained, long-term fertility. Fava beans, crimson clover, hairy vetch, and field peas can produce anywhere from 3 to 8 tons of biomass per acre in a single season when grown densely. These annuals establish quickly, fix nitrogen aggressively, and can be incorporated into the soil at their peak biomass stage, typically just before or during flowering. For those with more space or a longer-term perspective, incorporating nitrogen-fixing trees and shrubs multiplies your biomass potential exponentially. Siberian pea shrub can produce over 2 tons of nitrogen-rich biomass per acre annually through regular coppicing, while also providing deep-rooted stability and wildlife habitat. Black locust, when grown densely in coppice systems and harvested on 3 to 5-year rotations, can produce astonishing amounts of biomass, often 10 to 15 tons per acre, while fixing substantial nitrogen throughout its growth. Autumn olive, despite its invasive reputation in some regions, is an extraordinarily productive nitrogen fixer when managed intentionally, producing prodigious amounts of biomass that can be harvested multiple times per season. The strategy for reaching 6 tons involves intensive planting of quick-cycling annuals combined with systematic harvesting of perennial woody nitrogen fixers. On a quarter-acre plot, you might dedicate half to a dense planting of fava beans and crimson clover, producing roughly 3 tons of biomass in a single cool season cycle. The remaining space could support a coppiced grove of Siberian pea shrub or black locust, contributing another 3 tons through annual or biennial harvesting. This combination provides both immediate fertility from the annuals and sustained long-term production from the perennials, creating a system that becomes more productive each year as the woody plants mature. Growing 6 tons of biomass requires more intensive management than traditional cover cropping, but the investment pays dividends that compound over time. Site preparation begins with ensuring adequate soil moisture and basic fertility. While nitrogen-fixing plants manufacture their own nitrogen, they still require phosphorus, potassium, and micronutrients for optimal growth. A soil test helps identify any major deficiencies that might limit initial establishment. Once plants are growing vigorously and fixing nitrogen, their fertilizer requirements drop dramatically as they become increasingly self-sufficient. Inoculation is absolutely critical for maximizing nitrogen fixation, especially when introducing legumes to soil that hasn't grown them previously. Rhizobium bacteria must colonize the root systems to form the nodules where nitrogen fixation occurs, and without the right bacterial strains present, your nitrogen-fixing plants become nitrogen-consuming plants instead. Commercial inoculants are, honestly, pretty inexpensive and simple to apply. You can just coat seeds before planting or, if you prefer, apply liquid inoculants directly to the soil. I make it standard practice to inoculate every single legume crop, even in well-established gardens, because it really does ensure optimal nodulation and, maximum nitrogen production. Density is, another crucial factor in achieving high biomass production. Traditional agricultural spacing usually aims for individual plant productivity, but when you're growing for biomass, you actually want maximum ground coverage and enough competition to drive plants to grow tall and leafy. So, for fava beans, I plant at roughly 4 to 6 inches apart in rows spaced about 8 inches apart, which creates a dense canopy that shades out weeds and really maximizes photosynthesis per square foot. Crimson clover and hairy vetch, on the other hand, can be broadcast even more densely, at rates of 20 to 30 pounds per acre, forming a solid mat of nitrogen-fixing plants. This intensive approach honestly produces way more biomass per unit area than conventional spacing, making that 6-ton goal totally achievable even on relatively small acreages. For annual legumes grown as green manure, the optimal harvest point is at peak bloom, when the carbon-to-nitrogen ratio is just right for rapid decomposition. Traditional tillage, quickly incorporates biomass and accelerates decomposition, making nitrogen rapidly available, but, well, it also disrupts soil structure and microbial communities. I actually prefer a no-till approach, using a flail mower or a sickle bar to cut plants right at ground level, then just letting the chopped material lie on the soil surface as mulch. This surface application protects soil structure, feeds surface-dwelling organisms, and still provides excellent nitrogen release as the material decomposes. The roots remain in place, creating channels for water and air while decomposing slowly and feeding deeper soil organisms. For woody nitrogen fixers like black locust or Siberian pea shrub, coppicing provides biomass while maintaining living root systems that continue fixing nitrogen year after year. I harvest branches during dormancy, chip them, and apply the resulting mulch around food crops, or, stockpile it for later use. The nitrogen in woody material releases more slowly than herbaceous legumes, providing sustained fertility over months or even years. The larger branches can be used for stakes, trellises, or firewood, while the leafy material and small twigs provide the most immediate fertility benefit. If you're ready to break free from fertilizer dependency and build truly living, self-sustaining soil, subscribe to the Living Soil Lab for more strategies that work with nature's wisdom rather than against it. Share this video with fellow gardeners and farmers who are ready to revolutionize their approach to fertility, and join our community of growers proving that the best solutions are biological, not chemical.